Okay, so here as a sample, I have taken a full or a complete binary tree in which we have vertices and edges like this. Vertices are labeled A, B, C, D, E, F, and G. Correspondingly, I have taken an array of size 7, and for making it simple, I have started the index of the array from 1 instead of 0. So while implementing it using a program, you will have to take care of that as well. You can easily manage it. Uh, for making it simple, I have taken this. Okay, here the elements or the vertices from the binary tree are entered into the array in the level by level order. So the vertices from the first level are entered first, then vertices from the second level, that is B and C, from left to right are entered, then vertices from the third level D, E, F, and G. So if at any particular point of time, if there is no vertex, for example, if this vertex is not there, and this edge is not there, then you need to keep this as blank, and so on. You'll have to enter into this array. So from this, you are pretty sure that you have entered all the vertices values onto the array. Now you need to think about how you are going to manage the relationship or these edges onto this array, so that for representing a binary tree using array or a linked representation, you need to maintain these two things. That is, you need to store the vertices and you need to store the edges, right? So the vertices are already stored. Now we need to say how you are going to store the edges. Here, by utilizing this sort of a structure or this level by level order structure, this uh, edges are already by default, the edges are internally managed here. Let's see that. So for example, the element A is at index 1 and its left child is at index 2, its right child is at index 3. So A is the root node and B is its left child and C is its right child. So you can see that B is at position 2 and C is at position 3. You take this element B, its left child D is at position 4 and right child is at position 5. Same like for at index 3, uh, left child is at 6 and right child is at 7. From this you can very well see this pattern. The left child is, if the index of a node or index of a vertex in this array is I, then the left child will be available at 2 into I position and the right child will be available at 2 into I plus 1 position. So as I've told, if you don't have a right child here or if you don't have a left child here, then you need to keep that as blank in this place, so that at 2 into I and 2 into I plus 1, that sort of a pattern is maintained. And so at a particular point of time, you would like to find out the left child or right child of an element, then you can go and check this position in this array. The parent of a node I can be obtained at floor of I by 2. So for example, the parent of G can be obtained by 7 by 2, 3. So at 3, the parent of the node G will be available. So by utilizing this sort of a representation, it's very simple, and the relationship or the edges are managed internally very well. So as I've told, you need to enter the nodes level by level into an array. And if you're starting your index from 1, it will be well and good. Otherwise, you'll have to manage it internally. So this is the formula for left child, right child, and the parent of any node. Any questions? So next we will start thinking about linked representation of a binary tree, which we will be utilizing mostly in our later discussions instead of array representation. In linked representation, for explaining linked representation, I've taken another example in which there are some nodes missing. For example, here the left child is missing, here the right child is missing, here the left child is missing, here right child is missing, and so on. So a linked representation means we need to create a node such a way that just like we have created in the case of a doubly linked list. So we should not get confused right with linked list here. Here we are not going to create a linked list. Linked list is a linear data structure. Here we are going to create a nonlinear data structure. Anyway, we are going to use the same sort of node here. That is, you have a pointer which is pointing to your left child. You have another pointer which is pointing to your right child, and you have a position to store your data element. For example, the structure of a node in this case it will be like this. This is same as the node structure which we have created in the case of a doubly linked list. Struct node, then struct node star left child. So it's something very similar to, or it's very same as that of a self-referential structure. So it can again point to a node. So this node is also of this same type or same structure. Int data is for storing this data element. Then you have another. So this node structure has got two pointers, one pointing to the left child, one pointing to the right child, and one particular data item which can be integer, float, or any data item or any complex data item, which how we are going to define. For the sake of simplicity or for understanding it better, we take it as an integer value. That's it. Okay. So if you create the same tree in a linked representation. This was our tree previously: 4, 2, 7, 1, 3, 9, 1, 1, and 8. Then your tree in the linked representation, it will be, you will be creating a node. It has got a left child, it has got a right child. Left child is another pointer to the same node. Right child is also a pointer to the same node. And here you can store the integer corresponding its integer value. In this case there is no left child, so this points to a null pointer. In this case also there is no left child, so null pointer. Here there is no left and right pointers, so left and right child, so both are pointing to null. Here also both are pointing to null, and so on. So from this it is very clear that if any one pointer is pointing to null, the degree of this node is 1. If both are pointing to null, the degree of the node is 0. If both are not pointing to null, then degree of the node is 2. So as you have seen, a linked representation is dynamically, we are going to create dynamically this node. As and when the requirement of a node comes, we'll be creating this node by using malloc or any other dynamic allocation mechanisms. So this linked representation will be created in heap part of the memory. Array representation can be statically or dynamically created. If you are using for array representation also, you can go for dynamic representation, or you can the example which I have shown was using statically allocated uh, array. So in this case, if there are n nodes, there will be n plus 1 null pointers. For example, here we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 nodes. Then you have null pointers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if you have n pointers, there will be n plus 1 null pointers. You can take it as a formula, something like so. If there are n nodes in your binary tree, then there should be n plus 1 null pointers, which is similar to the formula which we have seen previously, that is number of external nodes is equal to number of internal nodes plus 1. Any questions so far? So we'll move on to another topic, namely full and complete binary tree. In yesterday's discussion, I have given a hint towards complete binary tree. That is, I have been discussing about something known as strict binary tree. So, as strict binary tree, as we have seen, it can have only in a general binary tree, it can any node can have 0, 1, or 2 degree. But in a strict binary tree, any node can have only 0 degree or degree 2. It cannot have a degree 1 node in a strict binary tree. So there I have mentioned that strict or complete binary tree. Uh, it's better if you differentiate between strict and complete binary tree. Here I'll explain about complete binary tree. Then we will try to compare what's the difference between strict binary tree and complete binary tree. And in some textbooks you will see the definition differently. We'll come to that later. Okay, so here I'm going to discuss about full binary tree and a complete binary tree. So what I have shown here is a full binary tree. Here the all possible nodes are available. For example, this is a binary tree of height 2. So height is equal to 0, height is equal to 1, and height is equal to 2. For with height is equal to 2, you can have how many number of nodes in a binary tree? Maximum number of nodes? 2 raised to h plus 1 minus 1, right? So 2 raised to 3 minus 1, 2 raised to 3 minus 1 is 7 nodes. So here we have all 7 nodes. So that sort of a binary tree is known as full binary tree. That is, you have all the possible nodes for that particular height. For example, if you have added one more node here, then the height of this binary tree is 3, 0, 1, 2, and 3. Then for a binary tree of height 3, you can have a maximum number of nodes equal to 2 raised to 4 minus 1, 15. But here you have only 8 number of nodes. So this is in that case, that is not a full binary tree, right? So what I'm trying to say is, in a full binary tree, you will have all the possible nodes in the sense for that particular height binary tree. What is the maximum number of nodes that is available? That many number of nodes will be there in the case of full binary tree. So if you check the array representation of a full binary tree, you can see that all the positions in the array will be filled up. So for example, in this case, A, B, C, D, E, F, and G, you have 7 nodes here. All 7 nodes are, oh, sorry, all 7 positions in the array are filled up. That will be the case of a full binary tree. This is an example for a complete binary tree. For a complete binary tree, the definition comes like this. Till height minus 1, this binary tree has got height is equal to 2. So till height minus 1, that is till this level, till the level just prior to the last level, it will be a full binary tree. That is till level 1, level 2, this is a full binary tree. And at the last level, the elements will be filled up from left to right. That is, there is a left child here, right child here, there is a left child, and a right child is missing. So still this is called a a complete binary tree. In that case, you can see that there will not be any gap between these what you know as the elements that is stored in the array representation. For example, if this was a gap and f was stored here, then you cannot say that this is a complete binary tree. So here what I'm trying to say is a complete binary tree is uh, height minus 1, it is a full binary tree. Then at the last level, the elements will be stored from left to right. That's it. So if you check the array representation, then it will be filled up till some position. So that is the case of a complete binary tree. A full binary tree is also a complete binary tree. So once again, a full binary tree means it contains all the possible nodes. A complete binary tree means till height minus 1, it contains all the possible nodes, and at the last level, it has got some few nodes, and that nodes are filled up from the left to right fashion. so that if you check the array representation, it will be up to some position, it will be completely filled up. And the last point of what I have made is a full binary tree is a complete binary tree. Now let's check whether this binary tree what I have shown here is a full binary tree or a complete binary tree. In this case, one right child is missing here, one left child is missing here. So the array representation will come like this: A, B, C, D. Then this is missing, and the right child E. So there is a gap between the last element and sorry, there is a gap between elements here stored in the array representation. So this is not a complete binary tree. So that's about full binary tree and complete binary tree. So I have shown examples for full binary tree, then complete binary tree, and these type of binary trees are not complete. Here, this is not complete because till last level it was full, but in the last level it is not stored. The elements are not stored from left to right fashion. If this element was here, E, and if this was not there, then this would have been a complete binary tree. And now let's come back to the strict versus complete binary trees. In yesterday's discussion, I have given a note that a strict binary tree is also called complete binary tree in some place. Some others use that uh, terms. That is, they use for strict binary tree, they use the term complete, and for complete binary tree, they use almost complete. Uh, but I prefer to use strict and complete as different. Whatever we have seen just now, we take this as complete. And strict binary tree, the definition is that you can have only 0 or you can have degree 0 or degree 2 in the case in for all the nodes. But in the case of complete binary tree, there can be nodes with degree 1 as well. For example, this node C, it has only degree 1. Don't get confused with all these things. We will try to compare the strict and complete binary trees now. So for example, this binary tree given in this figure, it has got A, B, C, D, and E, this many nodes. So the array representation will be like this. From this representation, you can very well say that this is not complete, but this is a strict binary tree. Because why? Because this node has got degree 2, this node has degree 2, B, D, and E. All the nodes are having degree 1, sorry, degree 0. So this is a strict binary tree, but this is not complete, right? Any questions? Am I audible?
Yes, sir.
Okay, so another example we'll take is yeah, this example. It has got the same number of nodes, but the nodes are shifted here, D and E. So here you can see that all the nodes are having degree 2, and D, E, and C, these nodes are having degree 0. These three nodes are having degree 0. So you can say that it is strict. That's once again this binary tree is once again strict binary tree. And what about its completeness? It's complete as well. Why? Because up to this level it's full, then in the last level it is filled from left to right. So you can say that in the array representation, up to some point there are all the elements are filled, and then there are blank. After that blank there is no element, so you can say that this is a complete binary tree as well. So this is strict and complete. This was strict but not complete. This is strict and complete. Let's take some other examples as well. Let's take this example: A, B, C, and D. From this array representation, you can see that this is complete, but this node has got only degree 1, so this is not strict, right? I think it is clear. So this binary tree, the sample binary tree here given is not strict but complete. And what about this? This is not strict and not complete. So I have given all the samples. This first binary tree which I have given was strict but not complete. This was strict and complete. This was not strict but it was complete, and this was not strict and not complete. I have shown all the possible combinations. I think the difference between strict and complete binary trees are understood. But some authors prefer to use strict as complete and complete as almost complete. Why? Because there are degree 1 nodes. So don't get confused with while reading some textbooks. Okay. So it's better if you use this convention which I have shown here. So next we will I'll try to introduce the tree traversals. The traversal algorithms we'll discuss in the next class. Uh, a tree traversal means visiting all the nodes in a tree. So how you are going to visit, or the order by which you are going to visit or the nodes in a tree, by utilizing that we can have different types of traversals. We'll be discussing about pre-order traversal, in-order traversal, and in-order traversal, post-order traversal, and level order traversal. So the pre-order traversal, the definition is this: you are at some particular node. Usually, you will be starting from the root node. The entry point towards the tree is the root node. So you will visit that node. Then you will be going to the left subtree in the same fashion. That is, you will be doing the pre-order of the left subtree. Once you complete the pre-order of the left subtree, you will be doing the pre-order of the right subtree. For example, if this was your tree, then this is your root node. Then you have a left subtree here. You have a right subtree here. So you will visit this first. Then you will call pre-order of this entire tree, which is same as which we have seen here. You will visit this node, then you will call, it has got a left subtree and a right subtree, so you will call pre-order of the left subtree. Once you complete the pre-order of this left subtree, you will call the pre-order of the right subtree. Once you complete this also, you will go for the pre-order of the right subtree of the root. So that in the from this definition, it's pretty clear that it's a recursive procedure, right? So you will be visiting this, then pre-order of the left entire subtree, which is same as the which is same as this, that is visit node, then pre-order of left, pre-order of right. So all these procedures which we are going to discuss are recursive, but we'll try to discuss its iterative procedures as well. In order procedure, there is only very small difference between all these traversals. In order procedure, first we'll be traversing through the left subtree, then we'll visit the node, then we'll be traversing through the right subtree. So this is pre. Pre means we'll be visiting the node first. In order means we'll be visiting the node in between. Post means we'll be visiting the node after visiting all the left and right subtrees. So in order traversal, you traverse the entire left subtree, then visit the node, then traverse the entire right subtree. Post order traversal, you traverse the entire left subtree, then you traverse the entire right subtree, then only you will visit the current node. So that is the general idea towards three traversals: pre-order, in-order, and post-order. Level order traversal means we'll be traversing through the tree level by level. So we'll be visiting this node at level 1, then all the nodes from left to right at the level 2, then all the nodes from left to right at the level 3, and so on, which we have seen just now. So level by level order, that is a simple traversal method. So we'll be discussing about these traversal mechanisms in detail. That is, its recursive procedures and iterative procedures. I'll be talking mostly about pre-order and in-order traversal, and the post-order traversal, you will have to do it your own. Let's take an example. So let's say you have these three trees of height 1. This is a tree of 3 nodes, this is a tree of 2 nodes, and this is a tree of another 2 nodes. Let's see what are the in-order, pre-order, and post-order traversal outcomes of these trees. So in pre-order traversal, just now we have seen that you will visit this node, then you will go to the left and pre-order of this entire subtree means you will visit this node and nothing left after this. So you will go back. So this is already visited. You will go to the right subtree. So the pre-order traversal of this is first you visit A, then visit B, then visit C. So A, B, and C. That is the pre-order traversal. Then what about in-order traversal? In the case of in-order traversal, we'll be traversing the left subtree first. So without visiting A, you will come to left subtree. Then there is nothing left after this. So what we'll do is we'll visit this node. So the node B will be visited first. Then go here. So in order traversal, this will be visited next. Then right subtree. So B, A, and C. In the case of post order traversal, traverse the left subtree, then traverse the right subtree, then visit the node. So it is first node that will get visited will be B, then the next node will get visited will be C, and the next node visited will be A. And the level order traversal will be level by level. A will be traversed, then B, then C. And that the with this example, the pre-order traversal is AB. In order traversal is first the left child, so BA. Post order traversal is also B and A. Why? Because there is no right side here. Level order traversal is also AB. So in the case of in this example, the pre-order traversal is AB. Why? Because there is no left child here. So this will be traversed, then go to left. That is, there is no left child, so go to right. So AB will be your pre-order traversal. In order traversal, there is no left child, so A will be visited first, then B, AB. Post order traversal. Post order traversal means the definition is post order of left child, post order of right child, then visit. So there is no left child, so post order of right child means B first, then A. Level order traversal once again A and B. We'll take a somewhat big example. It has got 7 nodes. So the pre-order traversal will be like this. Visit this node, then you go for this left subtree. Then once you complete this, then only you go for the right subtree. So pre-order traversal will be A. A is visited. Then you come here with once again calling pre-order traversal. So this will be visited first. This is visited. Then you go for its left. So this will be visited D. Nothing after this. So what you will be visiting next is E. So it will be B, D, and E. This is the order. Then you go for the right hand side. So this right subtree. C will be visited first, then F, then G. So the total visiting pattern will be A, B, D, E, C, F, and G. What about the in order traversal? In the case of in-order traversal, this will not be visited initially. First traversal will be transferred to this. So you will be visiting, or you will be calling the in-order traversal to this left subtree. So this, in this left subtree, this once again will not be visited. You will go here. There is nothing after this. So what will happen is this will be visited first. So the first node will be visited, it will be D. Then you go here, next node, then E, then A, D, B, A, E, A. Then you go to the right subtree. In the right subtree, you will be visiting F first, then C, and then G. So D, B, E, A, F, C, G. That will be the in-order traversal order. And in the case of post-order traversal, I think now it's very clear. You can very well do it with pen and paper. How to do post-order traversals, pre-order, in-order, and post-order. I'll just briefly explain. Post-order traversal means first the entire left child, then the right child, then you will be visiting A. So A will be visited last. That is clear here. A will be visited last. So here also you will be visiting left child first, then right child, then the root node. So D will be the item visited first, then E, then B. So D, E, B. Then you come to right child without visiting A. So F will be first visited, then G, then its root node, then its corresponding root node. So F, G, C, and A. So that's how post order traversal will be done. Now you already know how level order traversal will be done. In the case of level order traversal, you will be doing it level by level. So the nodes will be visited in the fashion: A will be visited first, then BC, then D, E, F, G. So that's all about tree traversals. I think the idea is clear. Any questions?